Hey everyone, welcome back, and today let's solve Leetcode problem 838 titled Push Dominoes. So there are n dominoes in a line, and we place each domino vertically upright, where in the beginning we simultaneously, meaning at the same time, push some of the dominoes either to the left or to the right. And after each second passes, each domino that is falling to the left will then push the adjacent domino to it on the left. Similarly, the domino falling to the right would then push the adjacent domino standing to the right of it, right? And where the vertical domino has dominoes falling on it from both sides, it stays still. Why? Because the forces kind of counteract themselves and they balance out. Because if I have equal forces on both my left and right ends, they'd cancel out, making me stay in the same spot, if you will. Right? And for the purpose of this question, we always consider that a falling domino expends no additional force to a falling or already fallen domino. So we're given the input string dominoes representing the initial state, where dominoes at any index I would be n, L rather would be an L, indicating that would be pushed to the left. Dominoes at index I would be an R if it was pushed to the right, and it would be basically a period or a dot. If it was just not pushed, it was staying still. And we want to return the string that represents the final state. So this is going to be a rather long kind of solution, at least in terms of lines of code. So I'm going to skip over the example here. It's rather straightforward here. You guys can read the explanation if you'd like. So basically, let's actually talk about the main observations that we really need to make to solve this problem in the most efficient solution. And it's kind of hidden in the problem statement and examples as well. Where effectively, we know that the effect of a falling domino, the effect of that it has on its neighbors, it would weaken the farther away it is. And so any domino that's pushed from far away, it might not even reach a standing one based on whatever the dominoes in the middle are. And so how can we actually model this behavior and calculate the forces applied for each domino? We can use a net force approach, basically the amount of force combined from the right side and the left side, and the net force approach. Where effectively the main idea of the high-level solution rundown, basically we'll have two different passes. We'll have a left to right pass to actually simulate the force from the right side, or for all the dominoes that have a force from the right or have a string R, and then a right to left pass to actually simulate the force going left. And we're actually going to store that net force at each position or index for each domino in an extra array, where a large positive force would mean a very strong positive R influence, or basically going to the right, or a large negative force would mean a very strong L or left influence. And if we have zeros for any indices, that just means those dominoes stay still. The forces around them, basically the net force of in total is going to be zero, right? There's no influence, it just stays still. And effectively, based on that net force at each position, index, or domino, if it's positive, we know it falls to the right. If it's negative, we know it falls to the left. If it's zero, it just stays upright. It's just balanced. Right? And to kind of further explain what I really mean by that net code, or rather net force, effectively, the way we actually assign forces is in our initial pass, when we go from left to right, we know that a string R, it would apply a high force because it pushes it to the right. So let's take a quick example. Let's say our force is 5. We know every dot afterward would get a decreasing force, 5, 4, 3, etc., 2, 1, until we actually hit an L. And from right to left, for all the dominoes having a force that go to the left, we know that left would apply a -5, and every dot before that would get decreasing force from -5, -4, -3, and so on and so forth, until we then hit an R, right, to kind of counteract or balance those forces, right? And so we then have to actually compute the net force for each position, kind of using that logic, where if, positive R would apply +3, and then L would apply -1, we know that the net force would be +2, and since it is positive, since it is a +2, we know that the domino would fall right, and so we'd have an R for that index or position domino for our output. However, if the forces cancel out, meaning they're zero, we know that the domino just stays still, and that's really the main kind of key idea that we really need to take away to solve this problem. So before I even get starting with iterating over the input array or beginning of any of my passes to get my net force, let's just first get the length of my input array dominoes. This is really just to help iterate over it because we're going to have so many different passes, and it just makes it easier to type out in the solution. And a little more elegant, if you will, right? Because we have so many different loops to iterate over the input. And let's actually build our extra list of forces, which is going to be our output, right? Forces. It's going to be all zeros initially, of course, with the same length as our input array dominoes, because it's going to be representing one kind of character or one kind of force, net force for each domino, right? It's going to hold that net force that acts on each domino that we calculate with our two different passes, and we'll build it in the third pass. So now, the first pass that we're going to do is going to be the left to right pass. This is basically for the right force, or the R force, for all dominoes that are going to the right, right? This is going to keep track of basically, all the force of dominoes going to the right, and we're going to do another pass for all the dominoes going to the left and sum that up as a net force, right? So effectively, the way that's going to work is, before I even actually start my for loop or do anything for there, let's first actually initialize my force. So let me get force, and it's going to be initialized to 0. Now the whole point of the force, basically, it's going to just keep track of the current rightward force as we actually go from left to right. And once we actually initialize that, we can then begin the iteration from left to right for the rightward force. So for I in the range of n, we know this is left to right, and so it's just a very standard loop in the range of n, where basically we iterate through each character of dominoes from left to right. And the first thing is, if our current domino, if it's falling to the right, we then have to set that maximum force or current force to be the index, right? And so the way we can check that is, if domino, I think it's domino, it's not domino, at the current index I, if we know it's equal to the string R, that means it has a rightward force, it's falling to the right. And if that's the case, we want to then update force to then be this n value, right? And this n value, again, is basically just going to be guaranteeing that the force is enough to reach any domino unless it's actually blocked, right? So to kind of reiterate, whenever we see an R, if we do see an R for the current domino, we have to then apply the maximum force. And to do that, we just set it to n, right? Where again, n is the length of our input array dominoes, the total number of dominoes that we have, right? Why do we set it to n? Because that guarantees, again, that the force is enough to reach any domino unless it's blocked. How do we know it's blocked? Well, if we see an L, right? And so let's move on to the next case here. In the elif conditional, else if, or elif in Python, dominoes at the current index, I think that's how you spell it, dominoes at the current index I, if we know it's equal to a left, if it's equal to a left force, well, then we have to reset our force, right? This is kind of like that canceling effect, and reset it back to 0. Why? Because any rightward force would get reset to 0, as a leftward push would cancel it out, right? Because again, we know that they basically cancel out if dominoes have left and right forces balancing it on both sides. That's basically like that canceling or balancing effect. Now, what is the else case here? Here we covered if the current domino has a right force. Here we covered if it has a leftward force. The else conditional would basically just cover all the dominoes that are periods, or basically all the dominoes that don't have any forces. They're, in other words, basically just still, or they haven't been pushed. They have no force in either direction. And if that's the case, we want to get our force, and we want to maximize it to be, of course, force minus 1, or just 0, right? Effectively, again, this is the case where the current domino is not been pushed, and there was a previous, or rather, I should say, if the domino is a dot, and we know that there was a previous R force, or rightward force, we then decrease it by 1, kind of simulating that weakening effect. However, we know that we can't have negative forces, and so if it goes negative, well, then we'll just make it 0, indicating that it doesn't have any force, because we can't have any negative forces. We can't have a force that goes below 0. Again, if the current domino is a period, or if it's a dot, and we know that the previous we know that there was actually a previous R force, we then have to decrease it by 1. I kind of glossed over this in my example, because that's kind of simulating that weakening effect, where you'd go from -5 to -4, basically. R would apply a high force, and then every dot afterward would get a decreasing force from 5 to 4 to 3. That's why we do force minus 1 for this specific dot, and so on and so forth, right? And believe it or not, once we actually do that, we're almost done here. We literally just have to update our forces, right? And so we'll add to our forces, kind of our own forces array that we built at this current index I. We'll add the force, right? Very simply, the current force is going to be added to forces at I, and this is just for the rightward force, right? We have to then subtract the leftward force to get the net difference, but we can worry about that in the second and third passes. We don't have to worry about that now, and that actually concludes our first pass, right? That's all we have to do for the rightward pass, for the initial pass. Now let's actually move to the left to right to left pass for the leftward force dominoes. And so, very similarly, we'll get a force, we'll get that to be 0. Again, we'll kind of reset it, right? We're resetting the force variable back to 0 to now apply the leftward force, and let's actually begin that iteration. And so again, this is right to left, and so it's going to be kind of a backwards for loop here. So for I in the range, or a reverse for loop, I should say. We'll start from the last index, which we know is n-1. We'll go up until the negative first index exclusive, or the 0th index, and we'll decrement by 1 each time for each index in each iteration. That's kind of a standard for loop, kind of reverse for loop syntax. We iterate from the last domino to the first one. Now, if dominoes at the current index I, if we know it's equal to NL, well then what do we do? Very similarly, we're going to get the force to just be N. And before I continue, let me just double check that I have enough battery. Yeah, I do. Okay, we're going to get the force to just be N, right? Again, very similarly, if we see that the current domino has an L, meaning it has a leftward force, since this is a leftward force iteration, we simply just apply the maximum leftward force, right? Very similar logic to the right kind of hand or counterpart logic of this solution. Now, what if dominoes at the current index I is this time an R? Well, then again, that's kind of like that counteracting or balancing effect. If it's an R, we have to reset our force to this time be 0. Why? Because we know that any ongoing R, or rather any R, would cancel any ongoing leftward force. Why? Because they balance each other out. And so we reset that force again to be back to 0 for the current index or domino I. And again, we of course still have to have the else conditional for if the current domino is a dot, meaning it doesn't have any force. And if that's the case, very similar logic here. We'll get the force and we'll maximize that to either be 0, because we don't want it to be negative, or force minus 1. We're still doing force minus 1 because the leftward force for a dot would just weaken like we did before for the right hand counterpart. And effectively, this is where we actually kind of have that net gain population, or that net force calculation. Forces at I has to, in this case, instead of being added to, subtracted by the force, because this is where we're subtracting leftward force, because leftward is negative, and that's going to give us the net force between the rightward force and the leftward force. It would just be the difference between those two, right? So forces at I is going to be subtracted by the leftward force of the current domino or index I. And that's actually completely it for the second kind of pass or iteration here to actually get all the leftward forces and for each domino. Now we want to actually build our result. And so to do that, I'm going to literally just going to call it result. This is effectively what we actually return as our output here. It's going to have the final state of each domino based on their net force, if they're positive, equal, a positive, 0, or negative, meaning if they're right, tilted to the left, or just staying still, if they're balanced, right? So now this is where we actually use what we built in the forces extra memory here. So for every F or force in the force input array, to actually build our result, we iterate through each net force value for each dominoes or for all dominoes. If the current force is greater than 0, we know that we can append to our result for this current domino an R, because we know that positive forces, or positive net forces rather, have R wins, or rather they have R forces. You can consider them to be R wins. What if F is negative, meaning F is less than 0? If that's the case, well then we very straightforwardly append for the current index or domino to the result L, because that would indicate that this has a leftward force. And finally, our last case in the else conditional, if in this case else F is 0, if the net force is 0 more specifically, well then we know that the domino would remain upright. Its net force is 0, meaning it has a balanced force between both sides, left and right. And then we append to our result for this current domino just a very straightforward dot, indicating that it is just an upright domino. And effectively, once we finish this building result iteration or pass, we then just have to join the characters into a single string and then return it from the result. So we'll return the string joint of all elements and the result list joined into one string, and that's going to be what we return as our output. So unless I made any syntax errors here, they should be accepted and there should be a valid solution. So let's go ahead and double check that. And as you can see, this really is just about as efficient as you can get it to be. So on a high level, how are we really solving this problem? Just to kind of quickly reiterate, because I know this video is getting rather long. Effectively, we're again simulating that physical process of dominoes actually falling by calculating the net force, meaning how much rightward or leftward force each domino receives, and then using that information to actually determine its overall final state, where we're again using those two different passes to get the left to right for rightward forces, and then the right to left for leftward forces, calculating that net force, and then telling us who wins or who has a stronger force at each spot in the domino. right? So for the runtime complexity here, even though we have two different traversals of the input array, since they aren't actually nested, they're completely separate. It's still going to be linear, meaning it's still going to be big O of n, right? Because of course constants and coefficients don't really matter in runtime complexity, and so as long as our for loops are separated, they're not nested, it's still going to be a big O of n or linear complexity. And for our memory or space complexity, very similarly, it's also going to be linear or big O of n. Why? Because we're really using that extra array forces here, and that's going to have size n to store the force at each index, and so this still is as efficient as possible for the context of this problem. And it's a very, very classic simulation and greedy type problem to actually kind of model, this real world physical problem. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.